All right, the next example I'm going to do has a moving boundary that is sort of impossible to remove from the problem by a change of coordinate systems. So this is a classic example. So this is a bellow. This is a pair of bellows. This is a device that's basically like, it kind of looks like an accordion. And when you squeeze on the upper and lower boundaries of this accordion-like object, it basically pushes air out of a tiny hole on the right-hand side here. And this used to be used, like, for example, to fan the flames of fires to get them really hot. So just as an example problem, what I'd like to do is use mass conservation and try to figure out the relationship between how quickly we squeeze the boundaries and what the velocity at the outlet is. So in this case, I'm going to say that there's an exit area on the right-hand side that, I think in practice this would come through like a tiny circular hole, but it doesn't really matter. I'll just assign an area to the amount of exit. And then for the accordion-like piece called the bellows, I'll say that there's a depth into the page of B. So that's meant to be sort of like almost like a pie wedge type shape, where you squeeze, the top and bottom portion of this figure, and the entire volume contracts. So there's no way for you to construe this problem in a way where it is steady state. So like on the inside of that control volume, obviously because things are deforming, this is not a steady state problem. So let's see how to handle that. So as with all these problems, basically like your first step when you look at a problem like this is try to figure out what it is you want and how you can get at it by choosing a good control volume. In this case, I'll choose the control volume that has the shape of the pie wedge that basically goes all the way up until just before the upper boundary, all the way down to just before the lower boundary, and then just follows the contours on the left side, and then contains the like a surface area that goes like through the exit. It turns out in this problem, because because the boundaries are moving, it's actually not enough to just draw the control volume. So that pie shape is actually not enough. You actually have to say how it deforms. And I'm actually going to solve this problem in two different ways, with two different ways that control volume can deform, and show you what I mean. So in this case, in quote version 1 of this solution, what I'm going to do is assume that the control volume moves, at least, so like as that upper and lower boundary gets squished together, I'm going to assume that the control volume is moving with that boundary at the same speed. So basically my control volume is going to contract over time. That is not the only way to do it, as I'll show you next time. I'll resolve this problem in the future with a different control volume. Because the outlet or the exit doesn't really move, I'll just assume that the control volume is fixed in that location, and then I'll assume that like on the left boundary, the control volume contracts with the fluid, or with the boundary, however you want to think about it. So at this point, what I'll do is write out the Reynolds transport equation for conservation of mass. So our statement was that if you follow the material, the rate of change of mass is 0. But if I write that on a control volume, that's the rate of change of mass in the control volume at any given time. So that's the integral over rho dV, plus the integral of rho times essentially the flow rate coming out of the surface is of that control volume. That should the total to be 0. So in this case, for our surface control volume, we need to be careful to use the relative speed or relative velocity in that integral, because the control volume moves. So just to be clear, the vector v sub r is the relative velocity. So the velocity of the fluid minus the velocity of the control volume. So the first integral is definitely not 0 in this case, because this is not a steady flow, and clearly the volume of our control volume is changing over time. So we need to actually evaluate that first integral. In this case, that is somewhat annoying, but not that annoying. So let's evaluate that first integral that has to do with the rate of change of mass in our control volume. So that is, ddt of the integral of rho dv. And then we can basically just use the geometry. So in this case, density is constant. So we really just need to calculate the rate of change of volume. What is the volume of that integral? Well, let's see. There's two little pieces that have to do with the pi wedge, what I would call the pi wedge, plus some additional constant because of the thickness of the exit. So at least for the upper, you can calculate the approximate integral as 2 times the integral of the upper pi wedge, which is the integral of r dr from r equals 0 to L and theta equals 0 to theta. Now there's actually two of those because there's like a top and a bottom, so that's the factor of 2, and then there's a depth into the page, and then plus, since there's a portion of that pi that might not actually, or there's a portion of our control volume that's not actually contained in those 2 pi wedges, you could potentially add some additional constant factor that's not changing over time. But when you take the derivative, that constant factor goes away, and you just get, after you do the integral, it's b times L squared times theta dot. So at this point, we've got our first integral evaluated. So that turned out to be rho times b times L squared times theta dot. And then we've still got this surface integral to do. The surface integral turns out to be pretty easy in this case because because I made the, in most locations, the relative velocity, so the velocity of the fluid minus the velocity of our control volume, is 0 because we made the fluid and the control volume move together. Wasn't that a nice trick? In fact, there's only one location where that doesn't happen, and that's where the exit is at. And so in this case, there's just this one location where we have to evaluate that integral, which is just at the exit. And in that case, you basically need to do the integral of rho times the exit velocity dotted with n times the surface area. In this case, the exit velocity is pointed in the same direction as the outward facing unit normal, so it gives you a positively signed velocity at the exit. And in fact, if you assume that the velocity is uniform over the exit, you don't actually need to do an integral here. It's just rho times v times the total area. And then you can invert that to solve for the exit velocity. And in that case, be careful with the minus sign here, but it's the velocity at the exit is minus b L squared theta dot over the exit area. Just to comment on that negative sign is there because if you think about it, if the rate of change of the angle is negative, that means that the angle is becoming shallower and the accordion or the bellow is contracting, and that is the direction which produces a positive velocity. So when theta gets smaller, it produces a positive viscosity, a positive exit velocity, and so that's why the negative sign ends up showing up. But it comes out of the math, really. All right, I'm going to resolve that same problem with a slightly different setup for the control volume, just so that you can see that how you choose the deformability of the control volume actually does matter.